going to begin looking at ratios and proportions and begin to utilize those in preparation for looking at similar triangles and similar polygons in the upcoming lessons. So to begin with, what do we mean by a ratio? Well, a ratio is simply a comparison of, in this case, one object to another. We can look at a side of this triangle and a side of this triangle and recognize that we have the first triangle has a side of 2 meters, the second has a side of 1 meter. The units cancel out, so we have a ratio of 2 to 1. We can either write it like that as a fraction, or we can write it with a colon and say it's a ratio again of 2 to 1. One of the key things when we are working with ratios is the fact that as we complete the comparison, all of the units need to cancel each other out. And so we're going to see here an example in a minute where we have to manipulate the units, do some unit conversion in order to get them to cancel out correctly. Let's take a look now at the ratio of this rectangle, specifically the width to the length. Well, the width of the rectangle is 7 feet and the length is 14 feet. Here again, we have the same units, they cancel out. So we have 7 over 14, which is a ratio of 1/2 or 1 to 2. Pretty straightforward, but again, the key thing here is to ensure that our units are canceling out. Because here we have an example. The first one is very straightforward. We have the same units, but in the second example, let's take a look at this. We actually need to do some unit conversion. We start by writing our given information as a ratio, but then we recognize what we have to do is do some conversion of feet and inches. So what we recognize is that we need inches on the denominator and feet here for the numerator. And so we show it as 12 inches to 1 feet. All of the units cancel, and we work out our ratio, and we see it's a ratio of 3 to 1. In this case, we had feet over inches in our initial measurement. Had it been the other way around, and had it been inches to feet, then we would have had to write the conversion as 1 foot to 12 inches. Again, we have to be able to cancel out all of our units so that our final answer is simply a numerical ratio of one to the other in comparison. For this example, number 2, we would have the same situation where we begin with 150 centimeters to 6 meters. We recognize that we need to do a conversion. Well, we need meters on the top, so we know that's times 1 meter is 100 centimeters. Centimeters will cancel, meters will cancel, and so now I can multiply across and I'll have 150 divided by 600, and I can simplify that in order to get my ratio of 150 centimeters to 6 meters. Key thing again is to correctly do our unit conversion so that all of the units cancel out. The way we can apply this in a problem is we have a situation where we know the perimeter, in this case of a wall, the perimeter is how far it takes to get all the way around this rectangular wall. But what we know about the length and the width is a ratio of length to width. Well, the first thing we do is identify our formula for finding the perimeter. And now we know that it's 2 times length, 2 times width. In this case, the length is a ratio of 9x to 2x, 9 to 2. We then work all the way out and we can solve for x, and we find that x is 22. What that does now is allow us to go back and look at the actual length and width of each of the the values of the rectangle itself. The reason we need that is the original problem is asking for the area where we have to know length times width. So once we have x, we plug it back in, we find length, width, multiply it together in order to find our area. The way we could have checked to see if our math was correct before finding the area is plugging the actual length and width measurements back into this equation and see if we came up with the perimeter which we were given, which is 484 feet. So there is a way that we could have tested our work. The same concept we can apply now in what is called an extended ratio. Basically, we're looking at a ratio of three different things to each other. In this case, we're looking at the ratio of angles within a triangle. So we have 1x, 2x, 3x, 1 to 2 to 3. The way then we can solve for x is we know all of those angles add up to 180. We solve and we find x equals 30. So now we know we have a 30, 2x is 60, 3x is 90. We have a 30, 60, 90 triangle. Simply plug the x back in and we can find the measure of each of the angles. Test that by adding them up, making sure that they equal 180 degrees. As we begin to work out our proportions and ratios, one of the things that we're going to need to begin doing is getting very comfortable cross-multiplying. So if I have a ratio of A over B, which is equal to a ratio of C over D, if I cross-multiply, I end up with AD equals BC. So I have to be able to work my ratios and my values algebraically in any way I need to in order to, at times, solve for what I'm looking for. Now, one of the things that we're going to be looking at is the fact that we may need to be doing that here with variables. And so if we take this and look at this equation, we set it up, but then we have to cross multiply the 3y and the y plus 1. Multiply it all out, and then we can solve for y. The way we can test it is y is 2. I have 1 over 3 on the left side, and I have 2 over 6 on the right side. Well, I know 2 over 6 is the same as 1 over 3, so I can test my value of y to make sure that I've done my math correctly. Here's a new idea in terms of the idea of geometric mean. And geometric mean is simply finding a number that satisfies the equation so that that works. And the way I find that number is, here I cross multiplied, but ultimately this is the equation I'm going to be working with. So the geometric mean, which I call x, is going to be the square root of two numbers, a times b. Now I can be given these two numbers and find the geometric mean, or I can be given the mean and one of the numbers and then solve for the other. I need to become familiar again with working with square roots. I know that if I want to get rid of the square root here, I would square both sides and I get back to x squared equals a times b. And if I'm looking for, say, b and I know a, then I would end up with x squared over a equals b. So we're going to be spending some time here working with square roots again, and there will be problems where you'll be asked to have it in simplest radical form, which means you're going to keep it as a square root. You're not simply going to be plugging numbers into your calculator. So we want to become familiar again working with square roots and then simplifying them down, keeping them in that simplest radical format. That's the end of the lecture on 6.1. You can find the exercise and the problem sets in Google Classroom or in Facts. We're going to continue working with proportions, and now we're going to look at different ways to set up our proportions and the power of cross multiplication, which is applying algebra to the ratios that we set up, we can see that if we have a proportion set up, A over B equals C over D, if I want to do the reciprocal of that, I can flip both sides and establish an equivalent proportion. So those are going to be equal sides. What I notice is ultimately, if I have A over B equals C over D, I can say AD equals BC. I can say A equals BC over D. What I have to remember is that I can cross multiply, I can divide both sides by a numerator, and I can change how my equation is set up, even though all of these are going to be valid and equal equations. So that's one of the key topics and one of the key things that we're going to need to really understand as it relates to the rest of this chapter, starting here in lesson 6.2. We can see another way here where we have cross-multiplied, as we were showing earlier, the B and the C. So we now have A over C equals B over D. Again, I can manipulate that equation using cross-multiplication in many different ways. The last thing is I can set up an equation where I can add each denominator to the numerator of the side because I'm in essence adding 1. Remember, if I have an equation which says A over B equals C over D, I can basically say A over B plus B over B, which is 1, equals C over D plus D over D, which is 1. I've added 1 to both sides. I haven't changed the value of my equation. And that's how I end up with A plus B over B and C plus D over D. So using different algebraic approaches, I can manipulate my equations in a number of different ways, which is going to help me then solve problems. Here I have a proportion which is established, and what I want to be able to do is write those proportions in many different ways. And so from the example, we can see that once I establish my initial proportion, I can do a reciprocal approach, I can exchange the means, or I can cross multiply, I can add the denominators to numerators. So I can adjust and manipulate all of those by starting with knowing this first proportion is true, substituting into that. For example, if I wanted to solve for x from here, I could simply say x is going to equal 4 times 10 over 8. And I've done that through cross multiplying. The sooner you get familiar and comfortable with cross multiplying, the easier it will be for you to approach many of these problems. Here's a situation where we're working down the side. I know B over D divided by, or BD divided by D over A is going to be equal to BE divided by EC. Once I set up my proportion, I can substitute in, and then I can simply solve for x. What I have to remember, though, is that dA is going to be 3, BA is going to be x, and that's going to leave BD to be x minus 3. So I can approach the problem that way and say BD is x minus 3 over dA is 3 equals 18 over 6. And then I can approach the problem that way in order to solve for it. So there are different ways I can set up the problem, and generally it's going to come down to the solution that you see that works for you first. One of the reasons we establish these proportions is because we want to be able to create a scale. And all a scale is simply some ratio of one image to another, oftentimes a smaller image to a bigger image. If you've ever done model trains or model airplanes, you buy them, you put together, those are called scale models because essentially what they've taken is the full size item, say an airplane, and they reduce everything down by the same amount. So they're scaling it down, and when you create the model, you're creating a scale model of that. The way we create the scale is we determine what the length of two of the items are, and then we know what ultimately the scale is going to be based upon that. A scale is not going to have dimensions. So we're going to have the measurement of one and the measurement of that same piece on the second drawing. When we establish our scale, the units cancel out, so we will end up then with a ratio of one to the other. The idea of a scale is used oftentimes in a map where we are representing a very large area on a piece of paper. And so, for example, for a map, we may have a scale that looks like this. 1 inch on a map is going to equal 26 actual miles. So the way you do that is then you would measure from your starting point to your ending point. You make that measurement, and you convert it using the scale in order to find out how far it is in actual distance based upon the map information that you have. The same thing occurs here when we have a scale model. In this case, we've got a scale model of Reunion Tower. The actual tower is 560 feet tall. If our model is 10 inches tall, we can then establish what the scale factor is between the model and the actual tower itself. Here in lesson 6.3, we're going to continue our work and take a look at similar polygons and some of the key pieces of information that we know to be true when polygons are similar. In the past, we've worked with the idea of congruency, and congruency looks like that. It means polygons have sides that are equal to each other. For the idea of similarity, we're looking at using just the tilde. And what we find then with similarity is that the corresponding angles in two polygons are going to be equal to each other. We see here the congruency piece. But then when we look at the sides, we're looking at the ratio of the sides. So again, if we're looking at polygon ABCD being similar to EFGH, the first thing we know is that the order of the vertices is important because it tells us which sides and which angles correspond to each other. Once we know that and know that they're similar, then we're going to know that the angles that correspond to each other are all going to be equal from one to the other polygon. So those four angles, and that's identified here. But then the ratio of the corresponding sides is what's equal. And all four sides, this compared to this to this side, and finally the last side. In each case, when you do one polygon, the side of one over the other, you're going to end up with a ratio, and that ratio has to be equal for all four of the sides when they are similar. Now the same thing is going to be true here for a triangle. Again, we begin by seeing that these are going to be similar triangles, and we're looking at R, S to T, X, Y to Z. So we pay attention to the order because what that does is it tells us the angles that correspond to each other, and the sides that correspond to each other. To ensure that these are indeed similar, we look at the ratio of each of the three sides together, and we see that they are all equal. Since we know that all three of the ratios are equal, we have proven that the two triangles are similar. And then again, if we were to look at the angles of that triangle, we would know that the angles would be equal as well. When we have two similar figures and we identify the ratio, that ratio, which is constant when we compare all of the corresponding sides, that ratio is called the scale factor. If we have a smaller polygon going to a larger polygon, so we're going from this one to this one, the scale factor is going to be greater than 1. It means they're getting bigger. If we're going from a larger to a smaller polygon, that scale factor is going to be less than 1. Once we determine the scale factor, and so as we look at this example, we're comparing the scale factor of this one to that one. And so we've identified the scale factor. The language is a little bit confusing. We're comparing this one to this one, which meant this is our starting point. So this would be number 1 and this would be number 2. That's why the scale factor here is going to be greater than 1, because each of the sides is bigger from number 1 going to number 2. If we were to go the other way, and we were to go comparing this to this, meaning we're going from the big one to the small one, it would be the reciprocal. So instead of being 5 over 4, the scale factor would actually be 4 over 5. We can tell then which way we're going because in one case the scale factor is greater than 1, in the other case its reciprocal is less than 1. So now what we can do is identify a situation where we want to ensure that these two triangles are going to be similar, but we have an unknown value for one of the sides. What we know is that for them to be similar, all three of the corresponding sides must have the same ratio. And so we know we're going DEF, MNP, so we know that those two sides correspond to each other. And then X and 20, those sides correspond to each other. So we've written our proportion statements here, substitute the information from the triangles, and then when we cross multiply and divide, ultimately we find that X is going to be 15. We can evaluate then and determine the ratio of 15 to 20 is the same as 9 to 12, which is the same as 12 to 16. So we found the value of X that enables these two triangles to be similar. In this example, the first part would be to find the scale factor. We're looking at a specific order here, A, B, C, D. So we're going that way, and we're going Q, R, S, T. It's really helpful that we draw our figures in the same orientation from one to the other so that we know the sides that correspond to each other. So in this case, we can look at 12 to 6. Scale factor of this to that is going to be 12 over 6, which is equal to 2. We can also call that 2 to 1. So we've got a scale factor of 2. Now that we know that's the case, we know that the relationship of X to 4 has to match that scale factor. So we know that X is going to equal 8. 12 over 6, 8 over 4, 16 over 8, 10 over 5, all of those have the same scale factor and show that these two figures now are similar to each other. We've been looking at similar polygons as it relates to the angles and the sides. One other thing that is true is that when we find the perimeter, and remember the perimeter is like taking a walk around our figure, when we find the perimeter of one of the polygons and compare it to the perimeter of the other polygon, the relationship of those perimeters is the same ratio as each of the sides. So essentially the scale factor then applies to our figures, the perimeter of the figures, just like it does the sides directly. Here's another example. We have a five-sided figure. We're told that they're going to be similar to each other. We're told the order A, B, C, so we're going like that. F, G, H, we're going like that. So we can find our scale factor of this to that is going to be 15 over 10, which is going to be equal to 3 over 2. Once I know that, then I can solve for x by applying this ratio to those, because I can say 3 over 2 is going to equal 18 over x. The ratio has to be the same for all of the sides because they are similar polygons. When we are kind of summarizing what we've been looking at, we know that polygons are similar. The ratio of any of the corresponding lengths has to be equal to the scale factor, and that has to be true for all of the sides. In the example right above this, we're comparing two triangles, and here the scale factor is 1. In that case, while the triangles are similar, they're also congruent because all of the sides are actually equal to each other. And we looked at those types of triangles previously in an earlier chapter. We've got another example here. We're told triangle TPR and XPZ are going to be similar to each other. And so one of the things that will be true is that the altitudes will also be similar. So once we identify the scale factor, then we can utilize that in order to find the altitudes and then find the entire length here of P to S. So that scale factor holds true for the altitude as well. In a previous chapter, we looked at using information and postulates like side angle side, side side side, to prove that triangles were actually congruent to each other, which meant each of the sides had the same measurement. Here we're going to begin using a similar approach, but again, what we're going to be focusing on is similarity. Now, similarity is talking about the ratio of sides, so the sides don't have to be equal to each other, but they do have to maintain the same ratio. And the first postulate that we're going to be looking at here is going to be angle-angle similarity. A couple things we know that when we're working with a triangle, we know that if two of the angles have the same measure, that the third angle has the same measure. Well, that can help us a little bit if we're looking for the measure of the angles, but it doesn't tell us anything about the size of the triangle. What we do know now is that if we have two angles that are equal in two triangles, as we see in this example here, K and Y are equal, J and X are equal, then by definition, those triangles are going to be similar. Again, that means that when we look at the ratio of all of the sides of these triangles, that ratio is going to be the same. We can use this approach to determine whether or not triangles are similar, and then if they are, figure out what the scale factor is. Well, in this case, we know that in both triangles, we have right triangles, and we're given a right angle. And we're given an angle here of 26 degrees and one here of 64. Well, because we know the sum of the three angles of a triangle have to equal 180, if this is 64, that has to be 26. 26 plus 64 is 90, 90 and 90 is 180. So now what we've done is actually proven that these triangles are going to be similar, and then we can evaluate their scale factor by looking at the ratio of the sides. What's important to note is that if we're writing our similarity statement, we know that angle C is going to be matching up with angle K. So since the order of our vertices is important, if we start with C, we go CDE, KGH. So that would be a similarity statement for these two triangles. We do not have to start with C and K, but again, the order of the vertices is critical because it tells us which sides will correspond to each other. We've got a couple of examples here, and we're trying to determine whether or not the triangles would be similar. In this case, we're looking at the smaller triangle and then the larger triangle. Well, what we do know is that we've got two 52-degree angles. So we've got one angle in each of the triangle. But the other thing we note is that angle A is the same for both. So in this case, we do have angle-angle similarity. In this example, we're going to go back to our old friend, the two parallel lines in a transversal, and let me redraw that a little bit better here. Let me draw it on this one. We know that alternate interior angles are equal. We know those two angles are equal. We also know that opposite or vertical angles are equal. So again, we've been able to prove that those two triangles are going to be similar because of having angle-angle similarity for both. In this case, we do know the triangles have different angle measurements. While these are not showing to be the same, what's actually true is that when all three angles are equal, it's going to be 60 degrees. Same thing will be true here, even though we're not told that this angle, say angle G, matches angle R. We're given enough information to know all of the angles are 60 degrees, and so again, they would be similar. When we're looking at CDF, we're looking at that angle, and then we're looking at that triangle. When we evaluate the triangles, again, we know 32 and 58. Those add up to 90. That's going to be 58. That's going to be 32. And so now we have enough information to be able to tell us that those triangles will also be similar. These are types of problems that we're going to need to begin getting really familiar with, because essentially we're going to be evaluating elements of a drawing from the information that's given. So if you were to read through the example, you know the sun is coming down in both cases, and it's casting a shadow. You've got a woman who's 5'4", and you've got a building. You don't know how tall that is yet. Well, you know how long the shadow is. The angle that the sun hits the woman and the building is the same angle. Plus, we know that this creates a right angle, so now we have two similar triangles. Because we know the triangles are similar, we know that ratio is going to be the same as that ratio, and then we're able to go through and solve for x. That would tell us then how tall this building is. As I've said before, let the math speak for itself. I realize that 5 foot 4 inches is nowhere near 80 feet, but we're going to focus on the math and the process and recognize that oftentimes the drawings are not going to be to scale. In lesson 6.4, we looked at angle of two triangles in order to determine whether or not two triangles could be similar. In lesson 6.5, we're going to be looking at side, 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 and side angle side to determine similarity. It's going to be the same approach that we used previously when we were looking at triangle congruence in an earlier chapter. But the difference here is that similarity is established by evaluating the ratio of the sides that correspond to each other. So in the first case, when we have side, side, side similarity, what we know is that the ratio of each of the corresponding sides, again, the order of the vertices matter. When we evaluate each of those sides, we have an equal ratio for all three of the sides. That tells us then that the triangles are going to be similar. So here in this example, we're trying to figure out if either this triangle or this triangle are going to be similar to ABC. And the way we do it is we have what I'll call a short side, a medium side, and then a longest side. And we look at the ratio of each of those. And in all three cases, the ratio has to be such that it's the same value. So when we compare the first two triangles, we find that it is. It's all 4/3. So we know that ABC is going to be similar to DEF. Now we're going to consider ABC and consider GHJ. So we set up our ratios, again, based upon short side, medium sides, long sides. And when we do this, we see two sides have the same ratio, but the third one does not. For this triangle to have been similar, this last ratio would have needed to be 1, so it would have been the same as the other three. Since the third sides had a different ratio than the first two here, we know that those two triangles are not going to be similar. We can use that now to help us solve for unknown sides of similar triangles. What we're trying to do is find a value of x that allows the two triangles to be similar. Well, again, we look at ABC to DEF. The first thing we note is that those two sides are going to correspond to each other, and that's going to allow us to set up our initial ratio. And then we're going to take these next two sides, BC and EF, and finish out our equation. Now we've got an equation with one unknown x. We work down our algebra and we can solve and find that x equals 7. What we have to do now is test that when x is 7, that those two sides are going to be proportional, and those two as well. They all have to have the same ratio. And when I plug x in and do the comparison here, then I can show now that all three of the sides have the same ratio, so that when x is 7, these two triangles are going to be similar to each other. I would use that same approach for these examples. I've got a short side, a medium, and a long, and I've got a short and a medium and a long. So I would start with my two short sides, 20 and 24. And then I have to see, is that going to be equal? We'll do our medium sides next, 24 to 30. And is that going to be equal to my longest sides, 26 to 33. When I evaluate each of those, I have to come up with the same ratio. And what I can tell is that this is not going to be the same as the first two. So I know those two triangles are not going to be similar. I'd use that same approach then to evaluate the other triangles to determine whether or not they are similar. We just looked at side similarity, and now we're going to look at side angle side. Very similar to what we've done before. We have to have two sides and the included angle, and if the included angle is equal and the two sides that create the angle have the same ratio, then we know that the triangles are going to be similar. So in this case, angle X is going to be equal to angle M, and now ZX to PM has to have the same ratio as XY to MN. If that is true, if this is true, and the angles are equal, then I know that the triangles are going to be similar as well. So what I want to do now is I want to summarize what we've been looking at in terms of how we evaluate similarity. We have angle-angle similarity. We know if two angles of two triangles are going to be equal, then they're going to be similar. We have side similarity. If we can show that all three of the corresponding sides have the same ratio, then those will be similar. And the last was side angle side. We know we have an angle and then the included sides. If those have the same ratio, then we can also use that to prove that two triangles are going to be equal to each other. So in this example, it's asking us to choose a method to determine whether or not the triangles are going to be similar. Well, let's see here. We don't know anything about parallel lines. That doesn't help us. We do know we have a pair of angles here, and those are going to be vertical or opposite angles, and those are going to be equal. So right away, I'm looking at the potential for side angle side. What I have to do is test whether or not the sides have the same ratios. And in this case, they do. Because the vertical angles are equal, I do know that those triangles are going to be similar because of side angle side. So I need to evaluate my figure and then determine which of the three techniques that we've learned is going to best apply. So if I have these examples, right now I have sides to evaluate, but I only have one angle, but it's a right angle. It's the same in both. And so I could use side angle side as my approach. I would have to test, does 18 over 24 equal 21 over 28? If so, then I know they're going to be similar because of side angle side. In this last example, I have three sides there, I have three sides there, and I would just evaluate to see if side works. I would have to do the ratio of short to short, medium to medium, and long to long to determine whether or not those two triangles would be similar as well. So again, I can be using either angle-angle, side angle side, or side side in order to show that triangles are going to be similar to each other. In lesson 6.6, we're going to begin to look at proportionality in triangles when we have a line across the middle similar to a midsegment, knowing that this segment in the middle is parallel to one of the other sides. So in theorem 6.4, what we see is two parallel lines, and we will be evaluating the relationship of this side to this piece over this side to that piece. When I write that, I have RT over TQ equals RU over US. Again, working down the sides of the triangle. However, by knowing how to cross multiply, I can also rewrite this RT over RU equals TQ over US. The reason I want to rewrite it that way is now, instead of working down the triangle, I'm actually going to be working across RT and RU, TQ and US. The key thing to remember is whether or not I'm working down or across is to be consistent with which segment I list first in the numerator, and then which segment I list in the denominator. So that, for instance, in this bottom part, I'm doing the top segment over the bottom and the top segment over the bottom. Both of these are going to be in the numerator. So that consistency is critical, regardless of whether or not I am working down the triangle or across. The converse of that theorem is that if I know those relationships are equal, that the proportions are the same, then I have proven that those two sides, that this segment and this side are parallel. So in one case, I am told they're parallel and I know the proportions exist. In the next case, I evaluate the proportions, and if they are equal, then I have a situation where they're parallel. So in the example here, what I want to do is find the length of this segment, knowing that those are going to be parallel. And so I set up my proportionality statement. I plug in all of the information I have, and I solve and find that RQ equals 6. Here again, I've worked down the side. I said RQ over QU, RS over ST. Let's see if I come up with the same answer if I work across. If I say RQ over 4, so I went from here to the opposite side, equals 9 over 6, and then I'm going to get RQ is going to equal 4 times 9 is 36 divided by 6, which equals 6. You can see I get the same answer here, showing that it doesn't matter whether I work down the triangle or across. Oftentimes it's going to be a function of what I see within the drawing that helps me know which way to go, and potentially even where the variable is that I'm going to be solving for. We have here actually a real world situation. Let's say I have two triangle pieces in this shelf, and I want to create a flat shelf for my shoes. Well, what I'm trying to do then is figure out, is where the shelf connects here going to be parallel to the bottom? If so, then I know that my shelf is going to be parallel. Well, I'm given some dimensions here, and so I'm able to evaluate my proportions. And unfortunately, what I find is that given the dimensions in the example, since the proportions are not equal, the shelf is not going to be parallel to the floor. And of course, now I've got a situation where my shoes are going to fall off the shelf. In this example, again, I'm looking for YZ, and I can decide to move either down or across, whichever way I want to approach it. And then in example 2, I can do the same thing. I can either work down or across, but in this case, what I'm trying to do is prove whether or not PS is parallel to QR, which means the proportions have to work out to be equal. And in the first example, I am told that they are parallel, so I'm able to use the proportions to solve for zy. This idea of proportionality, we've been looking at just a triangle now and two parallel lines, holds true when I have multiple parallel lines and transversals. And what's interesting is that in this case, we are looking at UW over VX. Excuse me. We're looking at UW over WY, VX over XZ. So we're working down the drawing. Let's see if I can actually work across the drawing the way I was doing before. So if I take UW over WY equals VX over XZ, that's my theorem. Now if I do some cross multiplying, I'll end up with UW over VX equals WY over XZ. You can see here now that instead of working down the line, I'm actually working across. So my relationships stay the same. I'm able to show that simply by cross multiplying, and I can solve the problem either way. In this next theorem, I have an angle bisector. It means it has bisected angle C into two equal angles. When that happens within a triangle, I bisected the angle. I'm creating proportions now that will hold true. AD over DB is going to be CA over CB. However, if I want to work instead of across my triangles, if I want to work within a triangle, I can still cross multiply, and I can go from this, let me zoom that in just a little bit. I can go from that to where I have AD over CA equals DB over CB. AD over CA. So now I'm kind of working within one set of triangles, DB over CB. All I have to do is be consistent. This side over that side is going to be equal to this side over that side. I start with my initial theorem, and I cross multiply, something that's going to be really important to be confident in doing for this, this lesson especially. And then I can rewrite my proportions. They're still going to be true and equal, but now I'm just going to be evaluating different sides. Here I have an example of 3 and a transversal. I know that angle 1, 2, and 3 are all congruent. So what that tells me is that these lines are all parallel because here to here, those are corresponding angles. 2 to 1, those are corresponding angles. Since the corresponding angles are equal, my streets here, Main Street, 2nd, and South Main Street, are all going to be parallel. And now I'm able to utilize the theorems that I just had to establish my proportions and then solve for, in this case, I wanted H to F. I wanted that distance. In this example, I'm told that this triangle, QPR, is going to be similar to this triangle. So now, what I'm able to do is use my relationships. What I have here is an angle bisector, and I'm able to use the theorem that I had previously. So I set up my relationships. RQ over RS, RQ over RS, PQ over PS, PQ over PS. And now I substitute in. What I have to remember is that RQ is going to actually be this entire distance minus that part. That's how I end up with 15 minus x. Once I see that piece of it, everything else I plug into the equation, and then I simply solve for x. Looking back real quickly on these examples, if I remember my 3 lines, they're going to be parallel because they are all right angles. I have my transversal. And so now I can look at my relationships. I can either go 16 over 9 is my unknown over this, or I can do 16 over that is 15 over 18. Whichever approach I recognize and I feel most confident with, I'm able to use because, again, when I cross multiply, I can change from going down to going across. Lesson 6.7 talks about the idea of similarity as it relates to transformations. All that simply means is by having what I'm going to call again as a scale factor, I can take a figure and I can create a transformation of that figure where all of the sides retain an equal proportion because I'm using a common scale factor. One of the key points to understand is that if my drawing is getting bigger, it's called an enlargement, and my scale factor must be greater than 1. If my drawing is getting smaller, if I was going, say, in that case from red to blue, it's considered a reduction. The drawing is smaller, and so my scale factor is going to be less than 1. It's always greater than 0. I need a positive number, but it's going to be less than 1. So greater than 1 is an enlargement, less than 1 is a reduction. And the scale factor then, in what we're going to be doing in 6.7, gets applied to every single coordinate point from one figure to the next. So in this example, I have a quadrilateral, and I'm given the 4 coordinate points of the quadrilateral. That's my drawing here in blue. What I want to do is create a transformation which has a scale factor of 2. The way I do that is I take that scale factor and I multiply every coordinate value by the scale factor of 2 to come up with my new set of coordinates. So 2 comma 1, when I multiply by 2, I get 4 comma 2. 4, 1 goes to 8, 2, and so forth. Now, what I'm able to do is plot all 4 of my new points, draw my figure, and what I've created is an enlargement by a scale factor of 2. Remember, it's an enlargement. Obviously, we see that from the drawing, but I knew that was going to be the case because my scale factor was bigger than 1. Here I'm starting with a triangle, ABC, and I've drawn that out. I know what my coordinate points for each of my 3 vertices are. And what I want to do is I want to create an image that has a scale factor of half of that. So I'm going to be creating a reduction. My scale factor is less than 1/2, but I take the exact same approach as before. I begin with my coordinate points of my initial figure, apply my scale factor to each case, and come up with a new set of coordinates. So 4 comma minus 4 when I multiply by a half, divide by 2, I end up with 2 minus 2. 8, 2 goes to 4, 1. So I'm using the exact same approach. In this case, my scale factor is 1/2. So my new figure is going to be smaller than the original. For this example, I'm given 3 coordinate points, and I don't have to plot my figures in order to determine my new coordinates for my new drawing. So if P is minus 2, minus 1, and my scale factor is 4, P is going to relate to L, and that's going to be minus 2 times 4, which is minus 8, minus 1 times 4, which is minus 4. The next would be M. My center vertex is going to relate to Q. So I go from minus 1 times 4, which is minus 4, and 0 times 4 is still 0. So you can see I apply this. I would do this also to get my last point in. And now I would have my coordinates for my new drawing, which is going to be a scale factor of 4, which is bigger than the original. For the second example, my scale factor is less than 1, so I'm going to go from a drawing down to a reduction. So my new drawing, once I apply 0.4 to all of my values here, is going to be a reduction from the original. Here's an interesting example because I have an entire initial drawing, but only part of a second drawing. What I have to do to figure out where the last point, which is going to be out here somewhere, in order to create my new drawing, what I have to do is figure out what my scale factor is, because I know R relates to G, Q to F, P to E. S is going to be to this value way out here, which is H, and I don't know what H is yet. But I evaluate each change, and I found that my scale factor here is going to be 3. If my scale factor is 3, I take my value of S, multiply by 3, and now I know where that last point would be at 12, 15 in order to finish my dilation. One of the key things to remember, and you'll be moving into the assignment soon, is that by knowing every point and the scale factor, I can find the new points without having to graph it because I'm doing the algebra and then ultimately simply graphing the representation.